Good morning, happy Thursday everyone. So today we're going to be working on BSTs, so binary search tree. And when I reference any BST, I'm always signaling binary search trees. Alright, so we're going to go ahead and do lead code problem 98, validate binary search tree. So let's go ahead and read the prompt. So given the root of a binary tree, determine if it is a valid binary search tree. A valid BST is defined as follows. The left subtree of a node contains only nodes with keys less than the node's key. The right subtree of a node contains only nodes with keys greater than the node's key. Both the left and right subtree must also be binary search trees themselves. Alright, so as you can see, let's look at the example here. The 2 is a root node, and so a binary search tree, the properties are that all the nodes to the left of the parent node, which is 2 right here, it's always less than. And then anything to the right of the parent's node, the value is always greater than. So as you can see right here, we have a root node right here of 5, and then we have a node value of 1 to the left of it, and we have a node value of 4, which matches the, but its right child value is 4. Oh, excuse me. So this 1, 5 is right here. The 1 right here, it does adhere to the properties of being less than. But as you can see right here, the node right here, 4, has to be greater than. But otherwise than that, if we look at 4, 3, and 6, this subtree within itself, 4 is a parent node and 3 is less than. So yes, true for the left side. So now we have to go right. And right, it has to be greater than, which is true here. But the fact that the node here at this parent root node is greater than 4, we're gonna go ahead and return false immediately for the second problem. And so what this is essentially saying is that they have to be less than or greater than. So the values can never be equal to each other. If you have a 2 and a 2, that breaks the rules immediately, and we're going to return false. So the best way to validate if it's a valid binary search tree is with min and max. So min, we're going to set it to negative infinity, and then max, we're going to set it to infinity as well. And what these are is going to be default parameters, and what we're going to do here is solve it recursively. So what we're going to do is, so let's go ahead and understand what our inputs are. Our inputs are going to be, we're going to receive the root node of the BST along with min and max values. We're going to return boolean, whether true if it's a valid, it is a valid BST, else false. As you can see, edge case, so one of the edge cases is that if a tree is empty, it is a valid BST. So this will return true. So automatically, if we receive an empty tree, we know automatically we're just going to return true, because we don't need to go ahead and traverse or anything like that. Okay, but otherwise than that, what indicates, as you can see, what indicates if would return false. So the base case, because since we're gonna solve this recursively, I know that with BSTs, it can be done with recursion a lot. You can use recursion to help you solve it. So with recursion, you need two cases that you have to implement for. A base case is when to exit the loop, and the recursive function to keep calling the loop until you reach the base case. Then it knows how to exit the function. So a base case here is that we would exit the function when if the root value is less than min. If we ever surpass because as you can see here in this example, oops, excuse me, I jumped over an example. So we have, let me make this example. Oops. Yeah, that should be okay. Let me this example here, 1, and then we're gonna say 5. Okay, so with this little binary search tree that I made right here, we always know that what we always know in using min and max is that it has to adhere to less than and greater than for the left side and the right side. So 2, we're gonna run through our first loop of 2 at 2 is gonna be measured to negative infinity, negative infinity, infinity less than 2, less than infinity, which is turned true. And now as we traverse through our left side here, our left side is going to still be negative infinity, and now we have 1 as our case here, and now 2 is our max. And is this still true? Is 1 still less than 2? Which is true. And then now we traverse through our right side. In our right side here, we are going to say is 2 less than 5, which is less than infinity, which is true. So where we use the min and the max, and we make sure that our node value right here is always in between. If we know that it ever passes like 2, 10, and 2 is less than 10, which is less than infinity, which this one is still true. So if we ever know that we break it, then we'll return false. So if the root's value or equal to, because a binary search tree, all the nodes are unique values, or if the root value is greater than or equal to max, we know that we can return false if it ever surpassed that, because you're breaking the binary search tree properties. So recursively, what we're gonna do is we are gonna keep calling the function on left subtree. We're gonna pass in the left subtree and compare it to max value, and then on the right subtree, compare it to the min's value, and it will return true if everything is true. Return true. Okay, so if the root node is empty, we're going to return true automatically. Otherwise, our base case that we're going to say is if the root dot value is less than or equal to min, or if the root dot value is greater than or equal to max, then we're going to return false immediately. Otherwise, what we're going to do is we're going to call the function. We're going to call on our function here is valid BST root dot left. Let's go. We're going to do the left subtree first, and then we're going to pass in the value of the node, and then we're going to compare it to max. And then now we're going to travel to our right subtree, root dot right, we're going to pair it to our min, always making sure it's greater than our min value, and this should be it. Oh no. Okay. Here I am saying, I remember. I always want to say dit value. Can I cheat and say this dot value? Or it won't let me. Okay, let's undo that. Root dot val, root dot left, root dot right. Okay, 213, it is expected false. If root dot value is less than or equal to min, min is equal to negative and max is infinity. If the root is empty, return true. If root dot value is less than or equal to min, or if root dot value is ever greater than or equal to max, we're going to return false immediately. 2, 2. It's going to pass in We're gonna go to our left. We're gonna go to our left. It's gonna get one. Oh, be right back.